Hey guys, Ben Pearson, the Roadster Tracker, and today I want to talk to you about something that's a little bit different than we normally do, but still worthy of some consideration. I want to talk to you about how we know what the exact shape of our planet is. And it turns out this was a very, very challenging thing to figure out. What we know today is that the diameter of the Earth as measured from pole to pole is 12,712 kilometers. And the distance from equator to equator at opposite ends is 12,742, a difference of 30 kilometers, which is roughly 20 miles. It took a long time and a lot of work to be able to figure out the difference between the two. And we only started to suspect this difference in the 1700s as we started to do large-scale surveys. So the first two large-scale surveys were done in Great Britain and in France, that they very carefully measured those two territories and two countries completely. But we still didn't have the ability to really accurately know what the shape of the surface was because those are two relatively small countries. One of those, though, was Great Britain, and they wanted to survey properly one of their holdings, which was the country of India. India is a very large country, and it's large enough that we were able to do that. As a side effect, and one of the reasons why this personally has a lot of interest to me, some of you may know that I'm a little bit obsessed with mountains. I have been studying, accounts of high altitude mountain climbing. I've even been playing a game called Climber: The Sky's the Limit over on my other channel. Really fun game, by the way. But we wanted to know exactly what the shape was, and we started to suspect, but not know, that the Himalayan mountains were the highest mountains on the planet, and those just happened to be close to India. See, those mountains formed when the Indian subcontinent pushed itself underneath Asia, creating a super high mountain range, and they are by far the largest mountains on Earth. The next largest would be the Andean Mountains in South America, the highest of which, though, does not even cross the 7,000 meter threshold, whereas there are hundreds of mountains that are more than 7,000 meters in the Himalayan general area. I know that they have some subcontinents, and we'll delve into that a little bit, but we'll just call them all the Himalayan, just for simplicity's sake. In fact, one little fun bit of trivia, it turns out that the mountain whose top is the furthest from the center of the Earth is not Mount Everest. It's actually a mountain in Ecuador that is named Mount Chimborazo, which is kind of a fun thing. It's only has a distance above sea level of 6 kilometers, roughly, a little bit more than that. But because it's so close to the equator and Mount Everest is fairly far off the equator, then it's a little bit further away from the center of the Earth. So, as previously mentioned, the correct way to do this was to do a survey. And the way that surveys work is very, very simple. In principle, though, to do a very accurate one, you have to do a lot of correction factors, which we'll talk here in a moment. Now, the basic principle is if you know the distance between 2 points of a triangle, and you know any two of the angles of this triangle, then you can very carefully and very accurately know the distance between all three. So what they did is they took two towers in India that they constructed, and they very, very carefully measured the distance between the two. They used a chain that was at a known temperature. They corrected for the temperature imbalance. They very carefully measured it between the different points, and they had a very, very accurate measurement between those two towers, down to really a couple of inches. Then they set up more towers, and they would mark out the distance between those two towers. Or make out the angles, therefore they can mark out the distances. And by also taking star sightings, you could figure out exactly where you were on Earth in terms of latitude and longitude. And by taking the distance above the horizon, then you could figure out the altitude of those points. And the horizon they would measure using a plumb bob. So basically a big weight that's on the end of a string will point straight down. Although we'll come back to that one. Don't worry about that. So they had the proposal to go and measure India. They thought at first it would take about 5 years. It turns out it took closer to 60, 70 years. And to some extent, it was being done for about 100 years after the fact. This is called the Great Trigonometric Survey. And for anyone who has studied anything about the Himalayas, they'll know that this is a very famous survey. The most famous thing that comes about here is the names of the 2 tallest mountains in the world. Mount Everest, which would have actually been Everest, is named after the second leader of the Great Trigonometric Survey, who was named George Everest. He may never have actually seen the mountain that he was named for, but he was involved somewhat in the process. He may never have actually seen the mountain that was named after him, but he was directing the survey and was certainly responsible for identifying it as the highest mountain. These people who were doing the surveying, they were not actually allowed into the country of Nepal, which is where Mount Everest is. Well, technically it's on the border between Nepal and Tibet, but regardless, they had to measure these things from a distance, and you can tell pretty quickly how far away a point is, but it's much, much harder to get its elevation accurately. You have to take into account a lot of different factors too. When they were getting close to Everest and the Himalayas, turns out you have just a little bit above sea level, and then you have these big giant mountains, and that is enough where a plumb bob doesn't quite point straight to the center of the earth. It's tilted just a little teensy tiny bit towards the mountains. And they actually had to correct for that. Periodically, they would manually measure the distance between 2 stations to make sure that they were getting accurate results. The results they actually, published in here in a survey that they were something like a kilometer off on one of their measurements, and that was really bugging them. And that is what it actually came down to, was the plumb bob was inaccurate because of the pull of the Himalayan mountains. I'd always kind of heard that that was something that needed to be corrected for, but I never understood why until I started looking into this. The name K2, which is the second highest mountain on the earth, was actually just a temporary survey name that they gave to the mountain. But it turns out that K2 is in such a remote area, and there are 4 other large mountains that are closer to any sign of civilization, that it was never really seen by humans until they started doing the surveying. Or if they had seen it, they would have thought it was just a tiny mountain that was much closer. It was only by this kind of survey that you could actually predict how big it was. So, fun little fact. Everest had been called Peak 15. They tried as much as they could to keep the names of whatever they called them locally. Everest, they could not find a name for that mountain because it can't really be seen from Kathmandu, which is the capital of Nepal and where most of the people were living at the time. A lot of later work revealed a Chinese name, and I can't remember the name of it off the top of my head, but just a fun little fact that that was probably the better name for Everest. So this survey, as it was continuing along, they would, come back in circles and do all kinds of things. And they had to correct for a multitude of factors in order to get accurate measurements. Not only did they have to measure the angles, they had to correct for things like the refraction of the atmosphere of the Earth. So it turns out if you fire a beam of light through a vacuum, it will go perfectly straight. But if you fire it through something that will slow down the light even a little bit, and the air will slow it down a little bit, then it will tend to bend a little bit. The most well-known thing for this is fiber optic cables, which you can fire a beam of light through and it will just go all the way straight through. But that has a pretty high refractive index. Air's is just a little bit above that of a vacuum. A vacuum is 1, air is like 1.01 or something really crazy low like that. But it is enough where over large distances you have to correct for it. And they really didn't have a good way to correct for this factor. So, because they just didn't know how much of it was, but they had to be able to measure it. And so the inaccuracies were potentially pretty high, but turns out with Mount Everest that the measurement they had was 29,000 feet exactly. But famously, their precision was actually pretty high, and they were pretty confident it was pretty close to there. So they added 2 feet to it just to make it sound a little bit more precise, because if you say 29,000, it sounds like you're rounding. And the person who did that, whose name I had forgotten to include here, was known as the first person who set 2 feet on the top of Mount Everest, because he added 2 feet to its measurement. The great mountains of the Himalayan had all been sighted, and it took a couple of passes to name them all. It's really, really challenging today to go back and see the original measurements of all of them. Up until the time of this survey and the concept that the Himalayan mountains might be the tallest in the world, we had actually thought that Mount Chimborazo was the highest mountain in the world. Turns out there's higher mountains as measured from sea level in South America, but they're much more to the south. Mount Chimborazo was in the more habitable parts, and it's really a conspicuously high mountain for that part of the world. So we had thought that the first one that kind of changed the mind was called Dalangiri, which was close to one of the first 8,000 meter peaks that had been summited, which was Annapurna. It's in the center of Nepal. It's one of the two mountains, along with Annapurna, that is contained entirely within Nepal. Most of them, these mountains are sharing borders with some of the other nations. The next one that kind of set the record was the third highest mountain, which is Kilimanjaro, I want to say. I should have written that down. But in any case, it is on the border of Nepal and India, and they thought that it may be the highest, but they started sighting and they saw Mount Everest in the background, but they noticed that you could see it over a very wide baseline. I've got an image here. It shows all of the different points where they sighted to get the measurement of Everest. They had a fairly good idea that it was probably the tallest, but until they could do all of these calculations to correct for the temperature differences, correct for the refraction, correct for the different pole of the plumb lob, correct for the shape of the earth, which they were able to understand, then they weren't able to really do that. And as a result, then they were able to correctly identify its height. And it turns out that most of these measurements were pretty accurate. Now, Everest, 29,002 feet, we know today that it is 29,035 feet. So that's a difference of, 1%? No, not even 1%, 0.1%, which is absolutely amazing considering that they did this with just a chain and some fancy survey equipment. And they did this without any fancy computers or knowledge of a lot of things we have today. Today, if you want to know the terrain of anywhere on Earth, we have satellites that go and do this. You don't need to do this. You can use GPS satellites to do this. And incidentally, if you want to prove that the Earth is round, it's really no more difficult to do than you can do the same kind of thing with surveying equipment. You could go and survey a couple of buildings from different locations. You could take star sightings to figure out exactly your latitude and longitude. And you would be able to see that the northern line, if you did accurately enough, would be, or whichever distance, if you're in the northern hemisphere, the northern line, the southern line for the southern hemisphere, would have a few more parts of a degree in the latitude and longitude than the southern one, and you could see the curvature of the Earth by doing that. It's entirely possible to do that kind of thing with some relatively inexpensive gear. I think surveying equipment these days costs something like $1,000. Out of the range of this channel, but hey man, if enough people watch this, then I will absolutely find a way to demonstrate using survey equipment what the diameter of the Earth actually is, because that would be a lot of fun. Unfortunately, I can't find any survey equipment for rent. And if you're in, say the Gulf Coast states somewhere and you have some fancy survey equipment that you would lend to me for a little bit, come talk to me. I'd love to be able to do some experiments with that to demonstrate the shape of the Earth. Meanwhile, thank you guys so much for everything. Let me know whatever questions or comments you guys have, and let me know if you like this kind of video. I know it's a little different than the space stuff we normally talk about, but it's always interesting. Thank you to everyone who likes and subscribes and comments on my videos. I really appreciate it. It always helps to get the word out there more. And thanks for everything, guys. Take care. We'll see you next time.